Hey everybody, Professor Tomney here from Chem Complete. Hope you guys are having a good day. If you've seen some of the previous videos that I've just posted online, I've announced there's going to be a lot of updates coming to the channel, including a lot of free content that I'm going to be providing you guys with. So one of my main goals for this channel is that I want to grow the channel so that it can be a serious supplemental income support, and at some point I would love to do this full time. But that's going to be a lot of work on YouTube and a lot of dedication. So I feel I need to offer quite a bit as a YouTube professor if I'm going to make that happen. But I'll have a separate video explaining some of the stuff that's going to be coming down the pipeline that I have. But today I want to discuss resonance, because while I've done videos on resonance before, I'm at that point in the spring semester right now where a lot of students seem to be struggling with the concept. And I see this come up usually towards the beginning of each semester. If I'm teaching Organic 1 that semester, there's a confusion as to what resonance is, what it does, what it provides for structures. And so we're going to kind of talk about, it's not a formal lesson, although you'll get a lot of material out of this. We're going to talk about what is resonance and why is it important today. So, to begin, what is resonance? So resonance is a phenomenon that happens when you're talking about a structure that has pi electrons and non-bonding electrons that are in given proximities to one another. So they have to be one atom or one space away from one another. And the structure has the ability to delocalize electrons over multiple sources or sites in the structure. So you could basically define resonance as a molecule's ability to delocalize electron activity or electron density over an entire structure. Okay, so what does that mean? If you think about the term localized, if something is local, something that's local is right in your direct area. It's right on top of your direct area, right? So if I say I'm running to the local grocery store, that means I'm going to the one in my direct area, the one that's local to me. So what does delocalized mean? It means spread out. It means far apart or not all concentrated in one area. So to delocalize electron activity means that I'm going to take the electrons that are present in the molecule and I'm going to spread them out between multiple atoms or bonding partners that are present there. And this is usually almost always a beneficial thing for a molecule. When you're talking about resonance, resonance adds stability to a molecule. It helps with taking formal charges and spreading them out over a larger area. And so all of these things are beneficial. They lower the amount of free energy in the molecule, which is a very stable thing. It adds stability to the molecule as a whole. So there's some rules that we can use to kind of guide ourselves with resonance. And probably the most important rule, although all of them are important when you're talking about resonance, but the first rule is that no specific resonance structure exists in reality. So what does that mean? Right? These resonance structures, they're imaginary. So why do we take the time to even start drawing them out and discussing them? Well, first of all, what that means, the fact that resonance structures are imaginary and they don't actually exist in reality, is that when we look at resonance structures, electrons are always in motion. So they're always going back and forth. Even in single sigma bonds, the electrons are not, a lot of students have this misconception that you have an atom here, and then right in between the atoms there's this bond. And the bond is static or non-moving. It just kind of links them together like a chain. And that is not correct. Okay, bonds are not static. They don't stand still. Electrons are constantly in flux between these hybridized orbitals that are sharing them. If it's pi electrons, they're going to be in p orbitals. But the electrons are moving back and forth if they're in this shared sort of proximity between the two atoms. And because electrons are always in motion, they don't stop off at one portion of the molecule and sit there even for a millisecond or two and then move to the other portion of the molecule and get batted back and forth. They're really, and sometimes we talk about it like that, but they're really a blend, right? They're a hybrid of all of the potential structures that are there. So let's draw a structure and take a look at this and see what we're actually referring to here. So let me bring up the whiteboard here. Okay, so let's start with a pretty simple example. Okay, if I take acetic acid, right? Acetic acid, when it's deprotonated, meaning the acidic proton is removed from this carboxylic acid, I'm left with this carboxylate ion, right? And the charge is found on this oxygen if I'm drawing the individual structure, because originally we had this OH, right? There was a base of some sort that came in, it grabbed the hydrogen, and these electrons, this set of two shared electrons, went to the oxygen. So now the oxygen, instead of having to share these, it has them to itself. And so that would be a surplus of electrons, and therefore this oxygen has a negative charge. So this is a perfect classic setup example for sort of resonance 101. So what happens here? Well, instead of this oxygen containing the full formal charge, which we have here, remember the formal charge, okay, a charge is really a representation of electron density. So if I have a formal charge of negative, it means there's extra electron density in comparison to what should be here. And if I have a positive formal charge, it's an absence of additional electron density that should be present there. So charges themselves, when we think about a charge, right, there's no real negative sign that's sitting above an oxygen or a positive sign sitting above a carbocation. It's really a mixture of electron density, and if we've got a surplus, we're getting on a negative term, and if we have a basically lack of electron density, you're going to be on the positive terms of formal charge. So what happens here? Okay, if we would like to view this from a resonance perspective, we write the sort of double-headed arrow here going back and forth, which shows that these structures are equivalent. Okay, and the way that this would happen from a mechanism, from an arrow flow point, is that these lone pairs would be deposited to create a new pi bond, and this pi bond would deposit electrons up onto this oxygen, right? So when we do that, remember carbon can only have 4 bonds at most. We cannot have more than that, and I'm kind of sneaking in these extra electrons here. All right, so then this would be the result, and the formal charge would be up on this oxygen. So what Rule 1 tells us for resonance is that neither of these structures exist in their entirety. What really happens is there's a blend of these structures, and so many times you'll see, now we don't often write it out this way in class, but many times what you're going to see in books or something else like that is something that sort of looks like this. Okay, and there's a negative charge in the middle. So what we're representing here is, you can see the pi bond, the double bond, shifts back and forth, and therefore what we're really looking at here is that the extra electrons are being delocalized or spread out between these two oxygens, right? So we don't have this oxygen taking a turn with the formal charge and then this oxygen taking a turn with the formal charge. Electrons are going to be spread out evenly, so that what we really have is almost, you can view it as half a formal charge here and half a negative formal charge here, which leads to this one formal charge being spread out between the two. Now this is a good thing, because formal charges are not particularly stable. We see them in a lot of intermediate structures, but we tend not to like formal charges hanging around in final compounds. Okay? And so if you have a formal charge, it's preferable to take the formal charge and spread the extra electrons or lack of electrons leading to that formal charge over multiple areas. Because if I have something, let's say a deprotonated methanol, just CH3O, there is nowhere for this formal charge associated with the oxygen to go. It can't be shared with the methyl group. There's nothing that can happen here. So this oxygen is solely responsible for the extra electron density. It does not have another partner to help spread this out. So one of the examples I always give in class and I find to be useful when explaining this is if you take something that's very high energy, my example is usually a very hyper child. And so if you have a hyper child that's screaming, bouncing off the walls, has had a lot of sugar, that is not a stable situation. That's a very high energy situation. So resonance is like the ability to have an extra adult present. And every single additional resonance structure is another contributor to that situation. Okay? So the more stable, grounded adults I have with that child, the better the situation is going to be. Whereas if I'm home alone and I have to deal with the hyper child myself, that places a lot of stress and strain on just myself as the adult and nobody else, right? As soon as my wife comes home and we've got two people that can help monitor that situation and diffuse it, we're in a better position. And then let's say that our two friends come over, right? And they have the evening available to help us out. Not that we're really good friends if we're doing that to them, right? But then you've got four people that are helping to diffuse the situation. So think about the hyper screaming child as the formal charge and every additional resonance structure that I pile on top of there as the extra ability to help ground and stabilize that bad situation, right? Because if there's four of us with the screaming child, we technically only need to deal with a fourth of the stress / responsibility. Same thing is going on with resonance. Instead of one oxygen taking on that formal charge, now two of them are. And if I had some other structure, maybe I could get 4 or 5 different contributors that are all helping in terms of that situation. Okay, so I think that helps to frame the idea that we're really, first of all, the electrons are moving back and forth. So it's a hybrid. We're all taking responsibility in that case. It's not that one person, one atom spends time with it and then bats it over to the other atom and back and forth. They're spreading it out equally because electrons are always moving and they're going to delocalize in order to get the lowest possible energy situation available. Low energy is good, and I always repeat that to students. Low energy, okay, sometimes you want high energy if it's an intermediate or something like that, but usually if you're in a state, you want to be in a low energy state. That's stable. High stability, low energy. Low stability, high energy. They're inversely proportional to one another when you're working with chemical structures. All right, so the second rule, the first rule was usually the biggest one to explain. The third one can take a little time too. The second rule that I like to follow when I'm talking about resonance is that when you deal with electrons, and this is very important, you can, if you're talking about resonance structures, you can only use pi electrons and non-bonding pairs. So let's look back at this example here, and we'll explain why that's important here in a second. Okay. So if you take a look at what's moving here, I have a lone pair or non-bonding electrons that form a new pi bond down here, right? And I have a set of pi electrons that are moving up in order to form a new non-bonding pair on that oxygen. Those are the only two things that are permitted to be moved back and forth. Now, it doesn't have to be a double bond. You can have a triple bond because those are pi electrons. We're talking about pi electrons and non-bonding electrons. But the big key here, okay, when you're dealing with this, is that you cannot move sigma electrons. So that denotes sigma, that's not a 6, okay? Sigma electrons. And that's because if you move sigma electrons, you're talking about single bonds. So if I break off this oxygen, if I say I'm going to move this bond right here and I'm going to reattach it over here and say that this is a resonance structure, well, there's multiple problems with this, okay? And the biggest problem right now is that if I moved this and broke it off and reattached it here, I'm now starting to talk about various forms of isomers, right? And a resonance structure, a lot of students get confused with this. A resonance structure or a set of resonance structures, they are not isomers, okay? When you talk about isomers, you're talking about stereochemical isomers, constitutional isomers, structural isomers. So an isomer is a way for me to rearrange the ordering or the spatial arrangement of the atoms and come up with a structure that is similar but not exactly the same when I'm talking about isomers. Okay, so isomers have different structural properties to them, whether it be stereochemistry, which is the spatial dimensions, right? So maybe I have a hydrogen on front of my molecule, and the next time I have a hydrogen in back of the molecule, even though they're attached to the same carbon. And then you can also talk about isomers from a standpoint of structural isomers, where, you know, I have propane and then I turn it into an isobutyl group, or something like that, right? An isopropyl group, where I am rearranging the branching or some other part of the structure of the atom like that. That is different than resonance. Resonance does not shift around any of the sigma single bonds in the structure. Those are off limits. Otherwise, you're talking about attempting to create isomers. Okay? Now, one of the other big issues here, which is going to come up in Rule 4, is that we now have a carbon that has 5 bonds. And so I can mention it now, even though I call it Rule 4, we can call it Rule 3. Rule 3, which goes along with this, is that all of your atoms need to be proper valence Lewis structures, meaning no carbon with 5 bonds, no hydrogen with 2 bonds, okay? It's not appropriate for me to turn around. Let me give you a new example here. Oh, come on. Is this not going to clear for me? All right. I don't know why this is not clearing right now. Give me a second, guys. I feel like I'm always having this issue now with this program. New. Don't save. Okay. So, technology. All right. So, what am I talking about? Let's take the same example again, right? If I've got something like, actually, let's use a slightly different example. If I've got something that looks like this, and then I've got, we'll say, a CH2 here, right? So now I have a carbanion, carbene. If I take this, and I say, all right, well, I'm going to move this in order to form a double bond here. And this will be one of my new resonance structures. Right? And I don't move the other pi bond associated with that oxygen. This is not an acceptable resonance structure. While this carbon has 4 bonds, this carbon has 5 bonds, and that's off limits. You are not permitted to give carbon 5 bonds. It doesn't have the d orbitals available in group 2 to do that sort of hybridization. And so this is not an acceptable resonance structure. You cannot do this. You are permitted to move this into a pi bond, but this needs to move up at the same time if that's happening. All right. So again, Rule 2, and again what I call Rule 4, but we can just call it Rule 3 as we're summing it in here, is that if you are going to create resonance structures, you need to move only pi electrons and lone pairs or non-bonding electrons when you're attempting to do this. And then the other thing is that you must always have valid Lewis structures. All right. So the last rule that I usually use for guidance, again, this would be Rule 3 for me. It's driving me absolutely nuts. It's like I wish my clear button would work. All right. So the last rule that I usually like to talk about is that not all of the contributors are equal to one another in every case. So what does this mean? It means that in some cases you will have 2 oxygens, right, or 2 carbons that are sharing the charge equally, or the electron density equally. And so in that case, you have what's called equal resonance contributors. But that's not always the case. Sometimes, like in the example we just saw, you'll have a carbon with a negative charge and an oxygen with a negative charge. So in a case like that, then you're looking at talking about one of them being a major contributor and one of them being a minor contributor. So in an example like that, the oxygen is going to be the major contributor because it is more electronegative than carbon is. So it's better suited for hosting higher levels of electron density around it, keeping that formal charge. So that doesn't mean the other resonance structure doesn't exist. It just means that it's somewhat limited in comparison to the oxygen one. Right? So the oxygen one is sort of the breadwinner. It's the major contributor. So maybe it's got about 70-80% of the electron density on its side, whereas the carbon only has 30 to 20% of the electron density on its side. And so we can use another example here that will help to show you this. Right. So if, let's see, what structure do I want to use for this one? Okay. So this is a structure I will oftentimes give on my quizzes when I'm in class. Right, so I've got this because it really gives a good variety here. So here's my structure, and this carbon contains an additional set of electrons, creating the negative charge that's present there. So what do we do with this? Well, this is one of the potential resonance structures. I can also move this charge over to the oxygen, and in that case the oxygen is going to be negatively charged. I'd have a double bond to the carbon that was involved with that, and then the nitrogen didn't end up doing anything in this particular contributor situation. Again, remember, we don't have individual resonance structures in reality. All of these are helping to pull some of the weight when we do resonance as a whole. All right, so the other resonance structure that is possible is if the nitrogen was helping out and the nitrogen took on the extra charge this time. So that's another potential. You've got 3 of them here, and technically these are also right with one another. So they're all resonance structures that would be contributing to the overall resonance of this molecule. So here, again, you're passing around a negative charge, so you want the atom with the highest electronegativity value. That's going to be the major contributor, okay? So if I have a negative charge, I'm looking for the atom with the highest electronegativity. So what contributors do I have here? I have a carbon that's contributing, I've got an oxygen that's contributing, and I've got a nitrogen that's contributing. So this guy would be the major contributor. This guy would be a mid-level contributor. We would technically call it a minor contributor because you have one major contributor, the rest are minor. But this is still mid-level compared to this, which would be the real minor contributor. Because if you look at the electronegativity trend, right, you go carbon, nitrogen, oxygen, and then fluorine, and it would be increasing as we go this way for the electronegativity trend. So this shows us that while the negative charge is being spread out between all of these, right, it is being spread out predominantly in this form. So you'll find most of the electron density from that formal charge up here. You'll find a decent amount of it over here in this form, and the smallest amount of it would be found in this form. But all 3 forms are still contributing. All right. Now, one of the things I wanted to show you, because I mentioned at the beginning of this lesson that I'm starting to increase some of the stuff I'm providing on the channel. What I have developed here is a Chem Complete study guide. Hopefully everybody can see this on the screen here. All right. So this is a recap of everything we discuss in detail and a little bit more. So it defines resonance, resonance structures, why it's important to learn, the rules of resonance, along with some examples in here. Okay. And then you have basically a conclusion or a summary of everything you want to take away from resonance. So this is going to be provided to you free of charge down below. If you click the link in the description, you will be able to download and use this material, a study guide on resonance. I've got one coming out for hybridization. I've got all sorts of different study guides that are going to be coming out. I'm really going to be amping up the channel in terms of resources to help you guys study. Okay? So remember to like, comment, and subscribe if you found this helpful. Subscribing will get you updates as I continue to release stuff. And if you like the video, it lets me know that I'm doing good. And if you dislike it, that's fine. I can always learn. I'm open to criticism. Okay? And then comments. People are starting to leave more and more comments. I'm trying to get back to them as the channel grows. We've got about 350 subscribers right now. If you leave comments, I will do my best to answer questions. Okay? Stay tuned. Look for other videos because I will be updating fairly often. And I hope to see you guys next time. Thank you so much for taking the time to learn with me today. And I'll see you guys then.